This is Geometry, Unit 6, Day 1. We're looking at similarity and transformations. As a review, we're looking at different transformations that preserve the length. Well, the transformations we've talked about before. Translations, rotations, and reflections. A translation is a slide. A rotation is a turn. And a reflection is a flip. Each of those types of transformations, they all preserve length. What that means is that the side lengths don't change when you activate this translation or rotation or reflection. Which transformations preserve angle measures? All of those again. Translation, rotation, and reflection all keep the same angle measures. The side lengths stay the same, the angle measures stay the same. The orientation is the only thing that changes, and that means the way that a triangle might point. Which transformations are rigid motion? When your lengths don't change and your angles don't change, that's considered rigid motion. It's real rigid. It's like made out of cement. It doesn't change its size or shape. So, which ones? Translation, rotation, and reflection. So each one of those would be considered rigid motion. With question number 4, if transformation preserves area, so if we're going to talk about just these types of transformations, a translation, a rotation, or reflection, if one of these transformations preserves area, is it always a rigid motion? If it's going to preserve area, then its size and shape is not going to change. It is possible that different triangles could have different dimensions with the same area, but when you change those sides, you're not going to have rigid motion anymore. These different transformations would not produce a different area. All of these, a slide, a turn, or a flip, would all keep the same area. Okay, when we're going to be looking on the second page, we have these different sails. So here we have figure 1 or photo 1. Down here we have photo 2. You can see that photo 2 is a reduction from photo 1. What we need to do is measure the different side lengths. So you'll take a ruler, use centimeters. We'll zoom in here a little bit. So I'm noticing that this is about 8.7. The AC is about 3.1. These are centimeters. And BC we're going to go over to DE, sorry. DE is 6.5. those seems to be the different size measures that we're looking for when we're comparing them to our table on page 1. So, for photo 1, which was the larger sail, what was the length of AB? 8.7 centimeters. What was it for photo 2? 6.1. AC for the larger was 3.1, and DE for the larger was 6.5. I don't think we've actually measured photo 2 yet. So let's flip back. To the second page. We'll zoom in. This is photo number 2. We'll measure we got about 6.1. AC is about 2.2. And DE is about 4.6. So, back on the first page on the table, we have 2.2 and 4.6. Now when we look at our ratios of photo 1 going into photo 2, or more appropriately said, photo 2 divided by photo 1, that's going to go in there approximately 0.70 times. Photo 2, which is 2.2, divided by 3.1, goes in there approximately 0.70 times. Now, if you look at the 100th spot, using your calculator, look at the 100th spot, and you'll see that the numbers are a little bit different. In a perfect world, these should come out to be exactly the same. But with the error of using a ruler or just the way the drawing is, are you measuring from the top of the line, the bottom of the line, are you measuring straight? Lots of different variations for why it's not perfect. But here we're doing pretty well. We're getting it all the way up to the 100th spot being the same. 4.6 divided by 6.5, and using our calculator, that is also 0.70. So that worked out just as expected. We would expect that if photo 2 is a reduction, here it is, photo 2 is a reduction of photo 1, and each photo find the length of AB. Well, we did that, right? The ratio of the length of AB for photo 2 and photo 1. Well, we did that. Repeat it for the other lengths. We did that for all the different lengths. Now we're going to measure the angles. So we're going to flip back. For photo 1, I'll look at angle 1, line up the vertex right in the center of the circle, line up the 0 right along the line, center of the circle right along the line, and I'm going to look to see where it crosses and that's just about 60 degrees. And if I come down here to photo 2 and I do the same measurement again, I should find out that it is also 60 degrees. Then we can move on to angle 2 back at photo 1. Take your time to get it straight so you know exactly where you're at. That looks to be a little bit more than 25, so we'll call it 26 degrees. And down in photo 2, a little bit more than 25 degrees, so 26 degrees. So back on our chart on the first page, we have 60 degrees for angle 1 for the big sails and 60 degrees for photo 2. Our ratio of that would give us exactly 1. 26 degrees, 26 degrees, would also give you exactly 1. So what that's showing us is when you have a reduction, that means it's going down proportionally, that the angles are going to stay congruent. Because remember, the angles still have to add up to 180, so they're not going to physically all get smaller. And this sum of the interior angles of a triangle has to be 180, so most likely they're going to stay all the same. The side lengths, they're not all going to decrease by the same amount. This one is decreasing by 1.9, but this one's only decreasing by 0.9. So they're decreasing in different amounts. On page 3, dilations are non-rigid transformations. That means they're not rigid, they're non-rigid, which is allowing them to change their size or shape. There's a function rule for dilations, which is x comma y, kx comma ky. You take your scale factor and you multiply it to the x and you multiply it to the y. So what we're looking for here is the different coordinates. So if we know that B's coordinate is 1 comma 5, then we know that B prime, if we have a scale factor of 3, is going to be 3 times 1 and 3 times 5. So we're going to be out at 3 comma 15. If you were to look at a straight line between those 2 points, it should line right up with the origin and go right through those 2 points. Also, if you looked at the slope, 1 over 5 up, 1 over 5 up, 1 over 5 up, it took 3 of those slopes to reach to your destination. There's different ways to help calculate where that point would be located at. Point A, 2 over 3 up. So the scale factor times 2, the scale factor times 3, so that's our A prime. Again, if you line up the A and the A prime together, it should go right to the origin. They should be collinear, all 3 points. So point C is 5 comma 4. So C prime is going to be 5 times 3 and 4 times 3. So now we have C prime. And remember, those C's should line up in a straight line right with the origin. So that would be the new image that is a scale factor of 3 from the original. Now down here at the bottom, we have a new shape. Triangle ABC is a little bit bigger. It's a little bit different than that one. So these coordinates, up here, remember, we have a scale factor. We often call that K, which is 0.5, or considered a half. The A is over 6 and up 8. So we're going to take that and multiply each of those coordinates by our scale factor. So half of 6 is 3, half of 8 is 4. To figure out B, we count over and up, and we see that that's 3/15. So to figure out the image location, we're going to take half of 3 and take half of 15. So we're going to go 1 1/2 over and 7 1/2 up. So that's going to be the B prime. C is located 16 over and 10 up. So half of that is 8 and half of that is 5. So that's the location of the image point for C. Remember that the point should be collinear with the origin. B's all line up, the A's line up in a straight line, and the C's all line up in a straight line. This is a dilation. The shape got smaller.